In preparation for talking about solving linear systems of differential equations with complex eigenvalues for the matrix, I wanted to address a couple concepts related to complex numbers and complex number arithmetic. So to start out with, let's talk about what we mean by a complex number. So a complex number is a number written like this: a plus bi. Here a and b are both real numbers. Either one of them could be 0. And the I represents a number such that I squared equals -1. Now, the reason I'm choosing to say a number such that I squared equals -1 is because there really should be two numbers if we want to be consistent with the mathematics that we've known from time immemorial, for which their square root is -1, and what one really means by the positive or negative square root of a negative number doesn't make a lot of sense. But in the textbook, or what's very typically done, we'll actually say I is the square root of -1. That's the idea. However, there really are, you should expect to have two numbers that would both square to -1, just like we have two numbers that square to everything negative. And the key issue is that which one you name as positive or negative I isn't really known. So, with the exception of electrical engineers, I is the typical lettering for this. There's always a way of visualizing complex numbers in the plane. So the C with a bar like this means complex numbers. And that is to visualize a number, not straight. We would let the real portion of the complex number, so the part that's just a real number a, is usually marked as a horizontal coordinate, and then b could be a vertical coordinate. And so the point a plus bi can be thought of in the plane as this a comma b, where we sort of have a real axis and an imaginary axis. And to emphasize what I mean here by this, I'll say that for every complex number z, we can define two quantities: the real part of that number z, which is just the number a, and the imaginary part of the number z, which refers specifically to the coefficient on the imaginary number I. So the real imaginary part of a number isn't bi, it's usually just denoted by the coefficient on the imaginary part. This is an important thing to keep in mind as we move forward. We're going to need to be able to use that distinction. So we notice that whether you talk about the real part or the imaginary part of a number, we are always talking about a real value. Now, to connect this back to the numbers in the plane in a couple more ways, let me show you a couple things about how complex numbers work. So first of all, if I add two complex numbers, a plus bi, to c plus di, because of the fact that a, b, c, and d are all real numbers, you can think of them as really scalars acting on these two coordinates. This is where the fact that they could be visualized in the plane is sort of meaningful. So we can just use associativity and distributive properties to reorder this as a plus c, adding the real parts, and plus bi plus di. And so we see that the real and imaginary parts of the numbers can be combined together. So when I add two complex numbers, here's the real part of the number is just the sum of their real parts, and the sum of the coefficient on the imaginaries becomes the new imaginary part. Every complex number has a conjugate. So the complex conjugate of a number of a plus bi is the number a minus bi. And very typically, we'll use a bar to indicate this. So if we have a number z that's denoted by a plus bi, then sometimes we'll use a bar over it to denote the complex conjugate. And what you'll note is that if you add a number to its conjugate, you do get just a real number left. Also, if you multiply a number by its conjugate, this is going to become a difference of squares, so you get a squared plus abi minus abi. Then we get a minus bi squared. So these two terms with the imaginaries on them cancel, and then when we square I, we're supposed to get -1. So we get a squared minus b squared times -1, or a squared plus b squared. So multiplying a number by its conjugate is a nice trick to eliminate issues of the imaginary parts, and in particular where this becomes useful is if we were dividing complex numbers. So when we multiply complex numbers, I showed you the example here for the case where the two numbers were conjugates, but generically we can multiply complex numbers basically as if they were polynomials, combining like terms, combining the I terms, combining the I squared terms, which then become real, and then combining the real terms. So here's the key example where using the complex conjugate becomes useful. Say I wanted to solve the following equation. Say I wanted to solve 3 plus 2i times x equals 5 minus I. Then I can divide. Complex numbers do have magnitude. There's no problem as long as it's not 0. I can divide by them. But the question is how to determine the real and imaginary parts of this number. Like, how do I even visualize what that number would look like in the plane if I was going to visualize it, or get a sense of how big it is? So to really do this, the trick is the following. I'm going to take that 5 minus I over 3 plus 2i, and I'm going to multiply the top and the bottom by the conjugate of the denominator. So 3 minus 2i. This is the same trick you may remember using when you had expressions that had surds in them, like with radicals, that we could rationalize the denominator in a similar way by using the right conjugate. So now I'm going to multiply out across in the numerator and the denominator. So I have 5 minus I times 3 minus 2i. And in the denominator, you'll recall that when we multiply a number by its conjugate, we get the real part squared, so that's 9, plus the imaginary part squared, or 4. And so you can go back and check the arithmetic and you can verify that that's correct for the same reason as we had happening up here. So now let's do that multiplying out for the bottom. Notice that 1/13 is just basically a coefficient in front here. So 5 times 3 would be 15. Multiplying the 5 by the second term, 5 by -2i, I get -10i. Now I'm going to multiply the inside, so -3i, and lastly I'm going to multiply the -i by the -2i. So I get a positive 2i squared. So now if I look at that, that's 1/13 times 15 minus 13i. 2i squared is really minus 2. So I find out that this number I was looking at the end of the day was actually 1/13 times 13 minus 13i. And by the way, I made this up on by hand, so it's not the case that these would always come out this cleanly. But in this case, we do actually end up with 1 minus I. This is how you can divide complex numbers. The reason we'll need to do this is that equations of this general form like this here aren't too far off from what it might look like when we're looking for eigenvectors. And that's something that is going to show up. If we have a complex valued eigenvalue, we're going to be multiplying coefficients by complex numbers, and so expressions like this very likely could show up.